Mihir Mirchandani, and today we'll be going over sorting. So let's sort out a few things about sorting. First of all, I'd like to go over insertion sort. So insertion sort is a very cool sorting algorithm that has a runtime of O(n)². It basically sorts an array by iteratively placing each element in its proper position by using swaps. So let's go over a quick example. Let's start with our leftmost number 5. Since there's nothing to the left of it, we can't swap anything with 5, so we move our pointer up. Next, our pointer is pointing to 4, and there is something to the left of 4. There is a 5, and 5 is actually bigger than 4, so we know that the 5 and the 4 are in the incorrect order, so we have to perform a swap operation between the two. Notice our pointer is still at 4, and after the swap, our pointer is now at 5. Next, we can't really swap 4 any further, so we increment our pointer. Now that our pointer is at 3, we look to its left neighbors, 4 and 5 of 3, and we see that 3 is less than both of them, so we have to perform a swap on both of them. First, we swap 3 and 5, so that 3 goes before 5, but we're still not done because 3 needs to go before 4. Finally, 3 is at the leftmost position where there are no more swaps. Notice our pointer is still pointing at the second index, now at 5. We move our pointer to the third index, now pointing to 6. 6 is actually bigger than its left neighbor, so we cannot do any swaps. So we move our pointer. 7 is bigger than its left neighbor, 6, so we don't do any swaps. We can no longer increment our pointer, so we are now done with insertion sort. Let's go over selection sort now. Selection sort is actually quite useful in that instead of swapping with neighbors one by one, what we can do is we can swap over large distances. To give you an example, let's sort an array of list of items by repeatedly finding the minimum element, right? So we find a minimum element in a subarray, and we put this at the very beginning of the sorted part. This runtime will be θn². So let's go through an example. Let's say we had 2 pointers, current num and current min. Let's place both of these at the very beginning of our list. Currently, our current min and current num are both pointing to the index at 5. What we do next is we move our current num pointer in one iteration, and we keep doing this until we find a current num that is smaller than our current min. Currently, our current num is 4, and currently our current min is 5, and since 4 is less than 5, we need to update our current min to 4. So we give current min the pointer to the new index of the smaller number 4. We keep using this current num to iterate, and notice we found a 3, which is even smaller than 4. So we update our current minimum again. Move our current num. Now current num is actually greater than current min, so we can't do any movement with our current min pointer. Current num is still greater than our current min, so we don't move the current min pointer. Notice we just found the minimum number in this entire array, 3. We swap this number with the very beginning of the sorted part. So we swap with 5, so 5 and 3 swap, and it looks something like this. Notice I highlighted 3 as a yellow square. The reason for this is because the index of 3 will not change. That 3 will always be at the beginning of the list. It is the minimum most number. It should go at the leftmost position. Now we shall find the minimum of the new subarray highlighted in gray. Notice no matter how many times we move our current num, we can never find something that is smaller than our current min 4, which means that 4 is in the correct position. We do this process again for the new gray subarray. We move our current num over and over again, and our current min still points to 5, our smallest number. Thus we highlight 5 in the correct position. We do this again Notice we can't swap because our current min is always at the correct position. Since we cannot move, this is the end of the sort. And finally, we have a highlighted, fully sorted selection sort array. Congratulations, you just learned insertion sort and selection sort. Let's go over some examples. In our worksheet, we have problem 4AI and 4AII. Notice that 4AI, selection sort, is the sort we just went over. 4AII is the very first sort we did, insertion sort. So keep that in mind when working through the problem. Okay, now that we've worked through the problem, hopefully, let's go over it. So in our first question, we're running a minimum base selection sort to see after how many swaps we get 6 before 7. Let's look through how many swaps that takes. On the right, we can see all of the swaps that are changed through each step. First, what we try to do is we find the minimum number in the array we are presented with. That minimum number is 0. This 0 swaps with the very first number, 4. Right? So you can see in our second iteration, 0 and 4 are swapped. Next, we look at this subarray 2 through 4, right? So we look at this subarray, and we find the smallest number, 1, right? And because 1 is the smallest number, we put that at the front of our subarray. So 1 and 2 swap, as seen here. Finally, we look at the subarray 2, 7, 3, 6, 4. 2 is actually the smallest number, so we don't do any swaps. So 2 is already in the correct place. Next, let's look at 7 through 4. 7 through 4 has a minimum of 3, right? Because 3 is in the incorrect space, it should go at the beginning, then 3 and 7 swap, as seen here. Finally, 7 through 4, 7, 6, and 4 is our subarray that we're looking at, and the minimum of this is 4. 4 should be pushed at the beginning of the subarray, so 4 and 7 swap, as seen here. Finally, in this iteration, 7 is after 6, and so we've done a total of 1, 2, 3, 4 swaps. So 4 is the correct answer. If you haven't already, I'd recommend you try 4AII for insertion sort. Okay, let's go over 4AII. In this problem, we no longer have the ability to swap over large distances when looking at a minimum. We only can swap with neighboring left nodes. So how do we approach this? Let's first start with our first example, 4217360. This is copied from this green block right here. First, we look at 4, and we see that nothing is to its left, so we can't do anything with 4. Next, we look at 2, and we see that 2 actually has something to its left that is bigger than 2, 4. So we must perform a swap operation. So in our first step, 2 and 4 swap. Next, we can go to 1, and we notice that 1 is actually smaller than 4, so we have to swap 1 and 4. But wait, 1 is not yet done because 1 is also smaller than 2, so 1 and 2 must swap. Notice it took us 2 swaps to get from 1 here to 1 here to 1 here at the very beginning, right? So now we have 1, 2, 4. That is incorrect order. Next is 7. 7 is also incorrect order because 7 is bigger than its left neighbor, which is good. However, if we move to 3, 3 is bigger than its left neighbor as well. Sorry, 3 is not bigger than its left neighbor. 3 is smaller than its left neighbor, and because of this, 3 must swap with 7. So, in our next step, we swap 3 and 7, so it looks something like this. And notice we're not done with 3 yet, because 3 is actually still bigger than, 3 is smaller than 4, but it's to the right of 4. And that is in the incorrect order, and because 3 is smaller than 4, we have to swap 3 and 4 again, right? So it took us 2 more steps to put 3 in the correct position. 3 can no longer move left because 3 is bigger than everything to its left, 1 and 2, so 3 is in the correct position, 4 is in the correct position, and 7 is in the correct position. Next, let's look at 6. 6 is actually not bigger than everything to its left. 6 is actually smaller than 7, for example. So we must perform a swap between 6 and 7. And at this point, we know how many swaps does 6 first go in front of 7. Basically, how many swaps does it take for 6 to go before 7, it takes 1, 2, 3, 4, 5, 6. So the correct answer is 6. Thank you all so much for watching. I hope insertion sort and minimum base selection sort is strong for your final exams. Best of luck. Take care.